A little over 400 years ago, a man named Galileo pointed a telescope at the sky for the first time. What we now call the scientific method was also developed around that time. So the science of astronomy as it's practiced today was born around 400 years ago. The year Galileo died, Isaac Newton was born. Newton is considered the greatest physicist of all time and one of the greatest mathematicians. Galileo's and Newton's enormous contributions to astronomy are undisputed. Every astronomy textbook covers these in detail. What they don't cover in detail is what happened before Galileo and Newton. Section 2.2 in our textbook is on ancient astronomy, but this topic isn't covered in a comprehensive way, and not at all in an inclusive way. There's a short paragraph on Mesopotamia, Egypt, and China, one on stone circles in England, and one sentence each on the Mayans and the Polynesians. And then there are about 30 paragraphs and figures on the Greeks. The rest of the world is not mentioned once. So why did the ancient Greeks get so much attention? They did contribute a lot to astronomy, but our education system is also extremely Eurocentric. I don't know what all you learned in social studies, but throughout middle school and high school, I only learned about the US and Western Europe. In college, I signed up for a history course called The Ancient World. Unit 1 was on Mesopotamia and Egypt, Unit 2 was on Greece, and Unit 3 was on Rome. That was the entire course. So to the folks who developed the course and the folks who wrote the textbook for it, the ancient world was just the ancient Mediterranean. Most of Asia wasn't part of the world, apparently, despite the fact that the majority of humans lived there. Most of Africa wasn't included. The Americas weren't either because Europeans hadn't gotten here yet. At my university, we had a separate department called Classics, which was just Greek and Latin. So Sanskrit, Chinese, Japanese, Persian, Arabic, etc. were not classical languages, apparently. Art meant Western art. Philosophy meant Western philosophy. Architecture meant Western architecture, and so on. This is what I mean by Eurocentric education. Today, some educators in America are starting to provide a slightly broader view. For instance, here is a chart called The Path to Newton. It starts with the Babylonians between 2000 BCE and 300 BCE, and then jumps to Greece. It shows a whole bunch of Greeks and their ideas, half of which we know to be completely wrong today. If something's in brown, that means it's wrong, and if it's in green, that means it's still considered correct today. Of course, wrong ideas are incredibly useful. Science is a process of filtering out wrong ideas and retaining whatever's left. But only wrong ideas by Greeks are shown. If you were Indian, Persian, Arab, or Turk, you had to be completely right, or at least partially right, to be included. Non-Greeks had wrong ideas too. They didn't just magically come up with right ideas without tackling wrong ones. And only people whose contributions directly made their way back to Europe are shown. The further you lived from Europe, the less likely you were to be included here. So a few Arabs, Persians, and Indians are included, but no one else. If we could devote the entire course to the history of astronomy, I would cover astronomical contributions made by different societies around the world. But we don't have time for that in this course. To keep things as simple as possible, I'll focus on just a couple of key figures and ideas. "2,500 years ago, long before this man named Ptolemy lived in Alexandria, Egypt, people already knew that the earth is round and he'd even figured out how big it is. But there was disagreement on whether the Earth and the planets went around the sun, or if the planets and the sun went around the Earth. There were arguments made in support of both views, but the most influential people favored an Earth-centered or geocentric model. They thought the sun, moon, and planets appear to go across the sky because they actually orbit the Earth. One of these people was Claudius Ptolemy. He lived in Alexandria, Egypt, which was then part of the Roman Empire. He had access to astronomical records from Egypt and Greece, and much older ones from Mesopotamia. These showed how long it takes each heavenly body to go around the sky. The sun takes on average 24 hours to go around once. Stars move slightly faster. They take 23 hours, 56 minutes. The moon moves the slowest. It takes 24 hours, 50 minutes. If the moon rises at 9 p.m. tonight, it'll rise at around 9:50 p.m. tomorrow night, and at around 10:40 p.m. the night after that, and so on. Ptolemy figured the moon moves slower than the sun because it's heavier. He thought Earth doesn't move at all because it's the heaviest thing in the universe, and stars move fastest because they're the lightest. And then there were 5 other objects that move faster than the moon but slower than the stars. They were called planets, which means wanderers. Since they move slower than the stars, they wander slowly from constellation to constellation. On any given night, they rise and set in the same constellation, but if you watch them for several months, you can see them drifting from one constellation to the next. The sun and moon are wanderers too. They just are way brighter than the other 5. Based on each planet's apparent speed, Ptolemy figured Mercury and Venus should be closer to us than the sun, while Mars, Jupiter, and Saturn should be further away. There was one big problem, though. Occasionally, a planet would move slightly faster than the stars for a period of time. All heavenly bodies move from east to west in the sky. Planets normally move slower, which means they slowly drift east relative to the stars from one night to the next, except when they don't. Occasionally, they drift west. This is called retrograde motion. Now that we know the Earth and planets orbit the sun at different speeds, we can easily explain this. Here's a figure showing Earth and an outer planet, such as Mars. The letters represent different times. From time A to time B, the outer planet appears to move normally, which, against the background stars, makes it look like it's moving up. But Earth is moving faster than the outer planet, and so it catches up to it by time C. This makes the other planet look like it's moving backwards in the sky. That's retrograde. By time D, Earth is raised further ahead, and so the other planet appears to have moved further back. So A to B is normal or prograde motion, B to C to D is the retrograde, and then by time E, the planet has returned to its normal motion. This is harder to explain if you think everything goes around the Earth, but Ptolemy found a way. He said planets make small loops as they make big loops around the Earth. Ptolemy was obsessed with circles and spheres. He thought heavenly bodies are perfectly spherical without any ups and downs, such as mountains and valleys. And he thought orbits should be circular. It would have been great if a simple circle would explain the motion of each planet around the Earth, but it didn't. But what if each planet made a small loop around an invisible point as it made a big loop around the Earth? That went a long way towards reproducing retrograde. The big loop is called the deferent, and the small loop is called an epicycle. Unfortunately, the center of the deferent couldn't be at the center of the Earth. It had to be at another empty point in space. And here's one more annoying thing. From the Earth, planets don't appear to move at a constant speed. But the amazing thing is, if you could view a planet from another point in space, called the equant, it would appear to move at a constant speed. and this equant happens to lie on the other side of the center of the different as the Earth and equally far away. I'm telling you all this just so you can appreciate the genius of Ptolemy. But don't worry about the fine details. It's good to know what an epicycle is, but you don't have to remember terms like different and equant. As Europe entered its dark ages, Ptolemy's model made its way east all the way to India. Ptolemy had used Euclidean geometry. The Greeks had been quite advanced in geometry, but the Indians were far more advanced in arithmetic. The number system we use today originated in India, as did trigonometry, algebra, and differential calculus. And meanwhile, the great Islamic empires of Persia, Arabia, and Turkey had also made great advancements in mathematics. And when they applied spherical trigonometry to Ptolemy's model, the model became messier and messier. And so they debated whether to reject it altogether or to continue refining it. During the Renaissance, one prominent European that chose to reject Ptolemy's geocentric model was the Polish priest Nicholas Copernicus. He favored a heliocentric or sun-centered model. He wasn't the first person to propose a heliocentric model, but he did it at an important time. Soon afterwards, Galileo would use a telescope to observe the skies, and his discoveries would completely disprove Ptolemy's geocentric model. I'll talk about Galileo in the next couple of videos.